The rules for designing overcurrent protection for the primary and secondary of a 208 volts to 208 volts Y/120 volts isolation transformer are indeed the same as this for 480 volts to 208 volts Y/120 volts transformer. This means that the percentages used to determine the appropriate overcurrent protection device sizes are consistent across these different voltage levels, assuming you are designing the transformer protection based on the National Electrical Code, or NEC. Let's delve into the specifics of these rules. For primary overcurrent protection, the general rule is to size the overcurrent protection device, such as a circuit breaker or fuses, at no more than 250% of the transformer's nameplate primary current rating. This allowance accommodates inrush current, which is a large surge of current that occurs when a transformer is initially energized. The inrush current can be significantly higher than the normal operating current, and oversizing the primary overcurrent protection prevents nuisance tripping during this event. It's important to note that while 250% is a common maximum value, local codes or specific applications may require lower percentages or specific types of overcurrent protection. Always consult the applicable electrical codes and standards for your specific situation. For secondary overcurrent protection, the overcurrent protection device should be rated for no more than 125% of the transformer's nameplate secondary current rating. This lower percentage on the secondary side is because the secondary current is more stable and predictable than the primary current, and there is less need to accommodate large inrush currents. Again, this is a general guideline, and local codes or specific application requirements might necessitate different sizing. In addition to the percentage-based sizing rules, there are several other important considerations when designing overcurrent protection for transformers. Firstly, overcurrent protection devices should be properly coordinated to prevent nuisance tripping. Coordination involves selecting overcurrent protection devices with appropriate time current characteristics so that the device closest to the fault will trip first, minimizing the impact on the rest of the electrical system. This is typically achieved through a coordination study performed by a qualified electrical engineer. Secondly, overcurrent protection devices should be located as close as possible to the transformer to provide adequate protection. This minimizes the length of unprotected conductors and reduces the likelihood of fault occurring between the transformer and the overcurrent protection device. Thirdly, the overcurrent protection devices should be of the appropriate type for the transformer. Circuit breakers and fuses are the most common types of overcurrent protection devices used for transformers. Circuit breakers offer the advantage of being resettable, while fuses offer the advantage of being relatively inexpensive and providing a high level of short-circuit protection. The choice between circuit breakers and fuses depends on the specific application and the desired level of protection. Let's now discuss how to calculate the primary and secondary currents of a transformer, which are needed to determine the appropriate overcurrent protection device sizes. The primary current can be calculated using the following formula. Primary current equals transformer volt ampere rating divided by primary voltage. The secondary current can be calculated using the following formula. Secondary current equals transformer volt ampere rating divided by secondary voltage. The transformer volt ampere rating is typically found on the transformer's nameplate. The primary and secondary voltages are also found on the nameplate. For example, consider a 100 kV ampere transformer with a primary voltage of 480 volts and a secondary voltage of 208 volts Y/120 volts. The primary current would be 100,000 volt amps divided by 480 volts, which equals 208.33 amps. The secondary current would be 100,000 volt amps divided by 208 volts, which equals 480.77 amps. Once you have calculated the primary and secondary currents, you can then determine the appropriate overcurrent protection device sizes using the percentages mentioned earlier. In this example, the primary overcurrent protection device should be rated for no more than 250% of 208.33 amps, which equals 520.83 amps. The secondary overcurrent protection device should be rated for no more than 125% of 480.77 amps, which equals 601 amps. Standard overcurrent protection device sizes are typically available in discrete steps, such as 400 amps, 500 amps, 600 amps, and so on. Therefore, you would select the next standard size that is equal to or less than the calculated value. In this example, you might select a 500 amp circuit breaker for the primary overcurrent protection and a 600 amp circuit breaker for the secondary overcurrent protection. However, these values are without the additional considerations mentioned above. Keep in mind that these are just examples, and the actual overcurrent protection device sizes may vary depending on the specific application and local codes. It is always recommended to consult with a qualified electrical engineer to ensure that the overcurrent protection system is properly designed. Regarding specific NEC articles, consider the following for transformer overcurrent protection. NEC Article 450 covers transformers in general, including overcurrent protection requirements. NEC Section 450.3 specifically addresses the overcurrent protection of transformers. This section provides detailed rules for sizing overcurrent protection devices based on the transformer's voltage, current, and impedance. NEC Table 450.3b provides maximum overcurrent protection device ratings for transformers with primary voltages over 600 volts. NEC Table 450.3a provides maximum overcurrent protection device ratings for transformers with primary voltages 600 volts or less. It's important to always refer to the latest edition of the NEC and any applicable local codes or amendments when designing overcurrent protection for transformers. The NEC is updated regularly to reflect changes in technology and safety standards. Let's discuss some common overcurrent protection devices used for transformers. Fuses are a simple and cost-effective overcurrent protection device. They consist of a fusible link that melts and opens the circuit when the current exceeds a predetermined level. Fuses are available in a variety of types and sizes to suit different applications. Common types of fuses used for transformer protection include time delay fuses and current limiting fuses. Time delay fuses are designed to withstand temporary overloads, such as inrush currents, without tripping. Current limiting fuses are designed to quickly interrupt high fault currents, providing a high level of short circuit protection. Circuit breakers are another common overcurrent protection device. They use a mechanical mechanism to open the circuit when the current exceeds a predetermined level. Circuit breakers can be reset after they trip, making them a more convenient option than fuses in some applications. There are several types of circuit breakers available, including thermal magnetic circuit breakers, which use a combination of thermal and magnetic elements to trip the breaker, and solid-state circuit breakers, which use electronic components to trip the breaker. Solid-state circuit breakers offer more precise and adjustable tripping characteristics. Ground fault protection is another important consideration for transformer overcurrent protection. Ground faults occur when current flows from a phase conductor to ground. Ground faults can be dangerous and can cause equipment damage. Ground fault protection devices are designed to detect ground faults and quickly interrupt the circuit. Ground fault protection can be provided by ground fault circuit interrupters, or GFCIs, or by ground fault relays. GFCIs are typically used for protecting personnel, while ground fault relays are typically used for protecting equipment. When applying overcurrent protection for transformers in specific applications, such as those involving motors or other inductive loads, additional considerations may be necessary. Motor starting currents can be significantly higher than the motor's running current, and the overcurrent protection devices must be sized to accommodate these starting currents without nuisance tripping. Similarly, other inductive loads can generate transient overvoltages that can stress the transformer and the overcurrent protection devices. Surge protection devices, or SPDs, may be required to protect the transformer from these overvoltages. Let's discuss the importance of transformer impedance in overcurrent protection. Transformer impedance is the opposition to the flow of alternating current and is expressed as a percentage of the transformer's volt-ampere rating. transformer impedance plays a crucial role in determining the magnitude of fault currents. A lower impedance transformer will allow for higher fault currents to flow, while a higher impedance transformer will limit fault currents. The transformer impedance must be considered when selecting overcurrent protection devices to ensure that they can adequately interrupt the maximum available fault current. The available fault current can be calculated using the following formula. Available fault current equals transformer volt-ampere rating divided by primary voltage divided by transformer impedance. For example, consider a 100 kV-ampere transformer with a primary voltage of 480 volts and an impedance of 5%. The available fault current would be 100,000 volt-amps divided by 480 volts divided by 0.5, which equals 4,166.67 amps. The overcurrent protection devices must be rated to interrupt this level of fault current. When replacing or upgrading transformers, it is important to verify that the existing overcurrent protection devices are still adequate for the new transformer. The new transformer may have a different volt-ampere rating, voltage, or impedance, which could affect the available fault current and the required overcurrent protection device ratings. It is also important to inspect the overcurrent protection devices regularly to ensure that they are in good working condition. Circuit breakers should be tested periodically to verify that they trip properly, and fuses should be inspected for signs of damage or deterioration. Proper maintenance of overcurrent protection devices is essential for ensuring the safety and reliability of the electrical system. In summary, designing overcurrent protection for transformers involves several important considerations, including sizing the overcurrent protection devices based on the transformer's nameplate current rating, coordinating the overcurrent protection devices to prevent nuisance tripping, locating the overcurrent protection devices close to the transformer, and selecting the appropriate type of overcurrent protection device. Additionally, it's crucial to consider ground fault protection, motor starting currents, transformer impedance, and the latest edition of the NEC and applicable local codes. Always consult with a qualified electrical engineer to ensure that the overcurrent protection system is properly designed and installed. The consistent application of these rules, regardless of whether you're working with a 208 volts to 208 volts Y/120 volts or 480 volts to 208 volts Y/120 volts transformer, helps ensure the safety and reliability of electrical systems. By adhering to the NEC guidelines and best practices, engineers and electricians can effectively protect transformers and connected equipment from overcurrent conditions, preventing damage and minimizing the risk of electrical hazards.